Okay, so in today's lecture, we should talk about bearing. There are many different kinds of bearing. This is the most common bearing you can see, where you have small balls inside, surrounded like a ring. And for the inner side and outer side, there are two different parts which clamps different metal balls to form this bearing. So let's take a look at the geometry and some of the common terms that was used for bearing. So usually when you buy a bearing, you care about the dimension. The outside, in some category, it will just say OD, meaning the outer diameter or outside diameter. Okay, and what's inside, the inner diameter, usually it's called a bore. Okay, and usually you have a shaft design. You should design your the diameter of the shaft to match the dimension of the bore. Okay, and it really depends on how tight you're looking for the connection between the bearing and the shaft. Okay, so you should design the tolerance properly. And the outer ring is usually fixed in some other geometry. Okay, so the shaft could be self-rotating on top of some kind of mechanical parts. That's pretty much you need to know. Okay, and because they are in the shape of rings, so the inner part is called the inner ring, the outer part is called the outer ring. Okay, and then there are some other detailed names of the parts, but we don't really need to talk about them. So also, when you design, you need to know the width. Okay. There are different types of ball bearings depending on application. Okay, but we don't talk about them too much. So it really depends on the choices of bearings. Of course, depends on some of the experience. But in this course, we particularly will teach you how to make proper calculations for the selection of bearings. Okay. From here you can also see not only we have ball bearings, we have those kind of roller bearings. Okay, and roller bearings usually can carry greater loads. So there is an important concept for bearing, which is so-called the life. And the life is going to be defined by the number of revolutions, so how many cycles it's gonna carry. But if the bearing is not carrying some load, you are just really playing the bearing like a toy, then it probably won't break, because it's not carrying much load. So usually when we talk about life, we also talk about how much load is being applied. Okay, and there is a number, very interesting, 10%. There is reliability involved in the life. So when you talk about life of a bearing, you need to specify what kind of load that is going to be applied to the bearing, and how many revolutions that you're looking for. After certain amount of revolution with certain amount of load, how much reliability you're looking for. Okay, so those three things are tightly related to each other. So number of revolution, and also the loads that you're carrying, and also reliability. So when you talk about reliability, typically for bearings, they are talking about 90%. So 90% reliable after a certain amount of revolution while it carries certain amount of loads. So that's why when in bearing design you commonly will see a term called L10. So the 10 represents failure rate. Because 1 minus 90% is 10%. So 10 is actually representing 10% of failure rate. So you can actually compute life in different values, like L5 or different numbers. So L5 will mean you are looking for reliability of 95% after a certain amount of revolution while it carries a certain amount of loads. Okay? So there's also some number called C10. So C is going to be representing the loads it's gonna carry. So L represent life and is in the unit of revolution. So L represent life. The C represents some kind of rating. So it's like how you score this bearing design. And you give this bearing a certain level of score. So, but what is the score? How is the score being defined? The score is being defined by the load, how much load it's gonna carry. Okay, so the relationship between life or revolution and the amount of load and the percentage of reliability will be described later. Okay, so before we start, you need to be aware what we're talking about. And in most catalog, it will define certain amount of revolution, such as 10 to the power of 6. Okay, so usually C10 is being given for certain amount of revolution. So C10 is like a certain amount of loads for reliability of 90% after 10 to the power of 6 revolutions. Okay. So it's like you want if you have 1,000 parts, 1,000 pieces of the exactly same bearing. After all of them being working for 10 to the power of 6 revolutions under the laws of C10, these 1,000 pieces will have a reliability of 90%. So 10% will fail, which means 100 pieces will fail. That's the rating. That's how much the manufacturer is going to tell you how strong my bearing is. If you carry this amount of load, working for this amount of cycle, 10% fails. But in reality, sometimes you don't carry this load, sometimes you don't operate with this amount of cycles, and sometimes you are looking for different levels of reliability. What do you do? So this chapter teaches you how to estimate how much load you can carry, how much gravity you can carry, how much cycles you can carry. So there are equations, there are models for these. Okay? Okay, so there's a concept. For every bearing, the manufacturer provides some kind of model. So this is definitely a model. So F represents the amount of loads, L represents life, and there's a power law. And the manufacturer realized, okay, the power is 1 over A, and A equals to 3 for ball bearings, A equals to 3.333 for roller bearings. Either it's a cylindrical or a tapered roller. And this value equals to a constant. Okay? So if this is true, that means I can have, this is a constant, right? So, like I said, if you have from the catalog, you have C10. That definitely means when I apply C10 to the force, multiplying the life, which is 10 to the power of 6, and 1 over A, this must be the same constant as well. So this value must equals to this. So you can get C10 from the catalog, and the catalog evaluates C10 based on 10 to the power of 6 revolutions. So in the future, when you choose the exactly same bearing, if you are looking for greater loading, then your life drops. If you are looking for longer life, then the amount of load you can carry drops. Did you see the trade-off? Okay, so by doing so, you can estimate all kinds of loading that you're looking for, or all kinds of life you're looking for. But if you want greater loads and greater revolutions at the same time, you may need to choose a better rating, a greater rating. So originally, maybe you choose one bearing with certain amount of C10, and you realize that is not enough. Then you may need to upgrade the design to a stronger one. But when you do that, sometimes the dimension changes. Because if you are looking for a stronger bearing, of course, it's gonna be bulkier. Okay, so make sure the usual design process is gonna be like you have a shaft design first, right? And then you are going to do what exactly we have done in the lecture. You are going to study the loads, how much loads it's gonna carry, stress concentration, and you realize, okay, over here I have a bearing. This bearing is going to carry a certain amount of load, so that you can have whatever design you're looking for. Then, with that bearing, you are moving on to this chapter and then study which bearing you are picking. And once you make a selection of your bearing, because of the bore dimension, you may need to change the dimension of the shaft. So everything is related, because maybe initially you don't have a decision of the shaft diameter. You just have an initial design. Due to that suggests you what kind of bearing you choose. But once you compute, once you pick up a proper bearing, maybe the bore dimension is not matching what you had earlier. So you will be making changes back and forth because they are so tightly related. Okay, so that's one way. Or you can use optimization if you want, but that requires more experience on optimization. I would say at this point, this will be one good way for you. Start with stress analysis. So you have a design, you have stress, force analysis, and then you have your decisions of dimensions and parts. Dimensions means you decide the dimension of the shaft and some other things, so that you realize the shaft is strong enough. And then you decide the part that is assembled together with the shaft. Once you have that, you may want to go back and check if everything matches your initial design. Sometimes you need to iteratively do this so that everything converges. Okay. So this is exactly what I mean. Any condition 1, this FL to the power of 1 over A will be a constant. So this value in condition 1 must equals to the same value, but in condition 2. Because of that, we can have the equation right here. That's exactly what I mean. Okay? But what's going on with this? So for many situations, you count the revolutions in the unit of RPM. Okay, so it's like every minute how many rounds? Rounds per minute, right? But in many of our calculations, we would like to compute in the real time. So you can do your conversion by modifying the revolution per minute to different units. But so you need to be aware. In general, the category will tell you what's the standard unit that we're using. So if you are using the unit of RPM, then if the category is not using RPM, then you need to do some conversion. This is how you can convert. Okay? So, there are situations where we have multiple rate, I think I don't want to talk about that. I will talk about this one. Okay. So here is a situation where you have, you are looking for different reliability. Okay, so let me see if they have this a particular drawing. Actually this one. Okay, so I will scroll up the screen. Okay. So what's happening is this line is if let's say we have certain values here. This is in the log I should say the coordinate. So over here, if this is log C10, okay, and if over here this is log 10 to the power of 6, and basically 6, right? If you are having the 10 as the base value, okay? So this line is representing reliability of 90%, right? So whatever I introduce over here basically is just like you are going to compute for example, different levels of different levels of loads. For example, if you are looking for greater revolution, this is log life, right? So if you are looking for greater revolution, of course, you can carry lower amount of loads. And if you are looking for stronger loads, then your life will be shortened. This linear relationship basically tells you how this equation looks like. But you are stick with 90%. How can you estimate the force and life with different level of reliability? So if you are looking for greater amount of reliability, of course, if you are sticking with the same amount of force, then your life will be shortened, right? So it seems like you may have different line right here, and this line could be reliability of, for example, 93%, greater reliability. So when I have same amount of loads, I may have a lower life. The issue is who's gonna model the different levels of reliability. So there could be different levels. So this is lower reliability, and this is higher reliability. Okay? So researcher will do experiments. Especially the manufacturer, they will test their parts, and then those circles represent some results from their experiments. That's why they realize for their product, the loads and the life has this kind of constant linear relationship. So they can start to collect data. For example, if I have certain amount of bearing pieces, and they are all carrying the force of C10. So when I reach this cycle, maybe I realize, if this is 95%, 5% fail. And then if I continue to operate and I realize, 2% more fail. So my reliability initially right here was 95%, and I keep on operating. 2% more fail, so my reliability drops to 93%. And when it reaches this amount of life, the reliability drops to 90%. So actually, with more experiments, I can collect more data. So I should be able to get a lot of data in the entire space. So they will build up this model, but different constant values. Okay? So they later on use statistical models such as this one. This is called a Weibull distribution. Weibull. I can show you how the Weibull looks like. Weibo. So Weibo distribution people sometimes choose proper coefficients, so the Weibo function probably looks like, I think they will use something like this. So a model that drops, you can, some kind of exponential function, okay? So they use some mathematical equation to describe how, I should move to that particular slide. Here. They try to find math models to describe how the value of reliability drops. So if you take a walk from here, if you walk right, and you realize reliability value keeps on dropping. They use some mathematical model to describe it. So along the walk, the horizontal axis basically is life. And when you are walking right, if the vertical axis is reliability, initially, without operation, you assume, actually, you should have 100% of life. All the bearings are new. They have 100% of life. With certain amount of revolution, some parts start to break, and you have some kind of trend like this. So after a certain amount of revolution, the reliability drops. For example, if this is 95%, and maybe up to here, 93%, something like this. And they want to use a mathematical model to describe this. So in the future, when they want to look for example, 94%, they probably didn't have data for 94%, but maybe that's exact reliability you're looking for. Then they have a math model for this intermediate point. Okay? So they use Weibo to do the job right here. Okay? So let me scroll down so you can see how they look like. So it's an exponential function. X right here is the normalized life. So it's the ratio of your current life and the life for 90%. So in our category, in the manufacturer's category, usually life for 90% is 10 to the power of 6 revolutions. Okay, so you can have any amount of life, so it's gonna be normalized as a value x. So you will have some reference numbers x0 and some parameters. This is basically describing the shape. Theta and the b describe the shape of this exponential function. So what are those values? Basically, the manufacturer will use experiments and then find the optimal fit. They find the best fit. So for different brands of bearing, the equation looks different. And there could be some other manufacturer who doesn't use Weibo function. They use a different function. That's very possible. But in general, for the decision of bearing, we have relationship, generally, we have relationships of revolution, loss, and reliability. And we have this linear equation in the log coordinate. But that model is good for a certain amount of reliability. So if you are looking for a different amount of reliability, they provide a second equation. In this textbook, they use Weibull model. Okay. I don't want to talk too much about reliability, so I think that's enough. Yeah, this is exactly what I mean. So the first line represents life reliability of 90%, and if you have a expected reliability, so RD is like a reliability for your design. When it's in the left lower portion of the rated line, that means you're looking for some reliability that is greater. Okay, and C10 you can get it from the catalog. So X10 right here basically is life 10, so it's a 10 to the power of 6. So you may have a design force and a design life. So you can, this part is basically telling you that in reality, you usually look for some specific force, specific life, and also specific reliability. And this is how they could be related to the values from the catalog. Okay? Basically, all these are calculations, let me see, on this line, supposedly. It's telling you, it's assuming for the design line, we still follow the same slope. So this is remaining a constant, but a different constant. If you are looking for 90% of reliability, this amount equals to a different constant. But if you are looking for a greater reliability, then this is still remaining a constant, but a different constant. Okay, so since you have 2 points right here, so you are sure the condition on B and the condition on D stays on the same design line so that you can use the same equation. This is what you can work on at the beginning. Then what else? Okay, so for the point B, from point A, you can use the Weibull model. They use the Weibull model to estimate point B. See, from AB. So the relationship along this horizontal line is going to be described by a Weibull model where you see reliability gradually drops. Initially, when there is no revolution, if this is 0, then when you carry, so right here reliability is 100%. So when it operates up to here, maybe 95%, and then reaches here, that's 90%. So the reliability drops, and that dropping is going to be described by the Weibull. Okay, so over here you can use a certain amount of shaped parameter theta and B, and some normalized parameter x0 to describe how this RD is related to the value R right here. And of course, different brands of bearing, different manufacturers will definitely show different profiles. So this is just a general approach. Okay. The rest are just math. Okay. So how about some examples. So like right here, it is showing some values provided by the manufacturer. So right here, it's telling you this particular bearing is having some weighable parameters over here, x0, theta, and b. And it's telling you the rated life is at 10 to the power of 6 equals to 90. So basically, should be 90%, I think. Yeah, 90%.